Good morning, everybody. All of you brave warriors, thank you for making it here at 8 a.m. for this session on long duration energy storage operations, value, and accreditation. I am Mahika Krishna from the Long Duration Energy Storage Council, or the LDES Council. You'll be hearing me refer to it as LDES henceforth because it's a bit of a mouthful to say it every single time. And I'm really honored to be moderating this panel alongside our speakers. Thank you very much to Deborah and to ESIG for giving me this opportunity. Really looking forward to a robust discussion today. So just to set the scene, I'm going to be sharing a couple of slides, hopefully not beyond 5 or 8 minutes. If I do, please feel free to do my job for me and tell me to move on to the actual speakers. But yesterday, I got quite a few questions about long duration energy storage in general, what counts as LDES, what doesn't, and also really what the main issues are when it comes to valuing an LDES asset. So just to provide a little bit of context, the LDES Council is a trade association. We're a nonprofit. We work with LDES developers and capital investors to essentially create a global marketplace for long duration energy storage. Our intention is to have a situation by 2040 where 5 to 8 terawatts of LDES is deployed globally. And this isn't just a climate imperative, it's an investment one. We want many countries, more than 60 countries, to be setting storage targets and also more specifically long duration energy storage targets. And we believe that there is $540 billion of system savings to be achieved through long duration energy storage. So this is just a little bit of a snapshot into the scale at which long duration energy storage deployment needs to grow for us to be able to hit that 5 to 8 terawatt mark by 2040. We're far from there at this point, but we look forward to addressing some of the key questions, fundamental questions in terms of power systems and reliability to be able to fairly value and recognize these assets and hopefully demonstrate the bankability that will help us get to this deployment target. So these are, as mentioned, some of the members that we represent. We have a fair number of technology developers, over 60 members across the ecosystem. And this diversity of members really reflects the breadth of LDES technologies, which I'll go into in a moment. But in terms of the applications of LDES, LDES isn't a single purpose asset. It's used to firm renewables. It's used to manage congestion. It's used to provide backup during extreme events. It's used to shift energy across hours, days, or weeks. And its versatility is its strength. I cannot say that word for the life of me. But here we will be focusing on the power to power aspect of it. So LDES as a grid scale transmission alternative, LDES in microgrids and distribution systems, and LDES in off-grid applications as well. Just to go through some of the technologies briefly, I'm not going to be spending ages on each of these slides, but there are 4 broad families of LDES technologies: electrochemical, chemical, thermal, and mechanical. So these are some of our electrochemical technologies available today, all clearly at various stages of commercial development. But the fact of the matter is these technologies exist. There are projects on the ground, and we need the right market signals in order to make these projects fully commercial and a reality. So some of the mechanical technologies include compressed air energy storage that are more on the commercial side of things. And we'll also hear some perspectives from traditional hydro and pumped hydro storage today on the panel. And then lastly, we have our thermal members and our chemical members. So all of these different energy storage technologies fall within the definition of long duration energy storage. And the LDES Council goes by any storage asset that can discharge continuously for 8 hours and up. That is our official definition. I've said it a lot these last couple of days. It's not necessarily scientifically rigorous. The US DOE has a definition of 10 hours and up. Some East Asian countries have much shorter durations that they consider long duration, from 5 to 6 hours and up. But this is what we go by, and therefore any storage system that can achieve these capabilities is considered long duration energy storage. So as mentioned, long duration energy storage has multiple different capabilities in terms of risk management, in terms of real-time operations and beyond. It's used to firm renewables, it's used to manage congestion, used to provide backup during extreme events, as grid stability and power quality services, black start services, etc. And most of the technologies within this range of energy storage can provide a variety of these services. So just to set the stage for the panel that we're about to have on accreditation and valuation of LDES systems, this remains an obstacle towards the deployment that we seek for long duration energy storage. And the biggest bottleneck isn't the technologies, they exist, as I mentioned, but the bottleneck is planning. And most systems, I think we know, treat a 4-hour battery and a 100-hour storage asset the same. And the frameworks that we use to accredit capacity and model resource adequacy don't reflect the endurance, flexibility, the temporal range, or the resilience that LDES provides. And in addition, we're working with the traditional resource adequacy metrics. We had a panel yesterday on resource adequacy and how that is going to evolve we had perspectives from different ISOs. But the fact of the matter is it's important to take a look at these metrics that are used to value resources such as long duration energy storage and reflect on the trade-offs between cost and reliability, or the value of preventing rare but severe events, which is where LDES specifically provides a lot of value. With that being said, I think we can move on to some of the framing questions for this panel. Since we have varying perspectives from our speakers today, I just wanted to help our audience keep these questions in mind. How do we capture the true system of LDES value accurately, including multi-day reliability and seasonal adequacy? What are some operational data and insights that could shape how we model and accredit LDES today, known as a very difficult resource to model accurately? And what are the right metrics when it comes to looking at LDES systems? So that being said, today's session has 4 critical perspectives that you will now hear. And I would love to call upon Gabe Miller, hydrologist from TVA, for his presentation.
Good morning. Thanks for braving the early morning with us here. I work for river management at the Tennessee Valley Authority, and I'm going to talk to you a little bit today about one of the oldest forms of long duration energy storage, which is conventional hydro. So I'm going to talk about how we manage our hydro system, and then also how we integrate and optimize our hydro system with our production cost model and the rest of our assets at TVA. So a little bit about TVA. TVA is a unique organization in the sense that we are a federally owned utility company. We were founded in 1933 as an act of Congress. And really the reason it was founded was to electrify the Tennessee Valley, which was very underserved at the time, to promote flood control, navigation in the Tennessee River, which had a lot of flooding issues at that time, then also to promote economic development for the region that was very poor at that time. And so this is a little bit of a picture of our service area and our watershed. So in the light is the TVA watershed, which is what I'm going to be talking about. And then in the darker color there is our power service area, which extends beyond the Tennessee Valley watershed. So we have 29 hydroelectric dams. We have 20 non-power dams. We have 1 pump storage facility as well. And then that hydro is about 9% of our total portfolio. The rest of it is made up by a mix of nuclear and coal and gas and some solar renewables as well that are coming online. So we have a 24/7 river forecast center in Knoxville, Tennessee, about 3 hours east of here. And that is where we manage our river system. We have a system operations center where we manage the rest of our assets in Chattanooga, Tennessee. And TVA also has a small office here in Nashville. So just talking a little bit about what goes into how we manage the river system, I want to kind of frame that as we get into more of the power modeling, because a lot of that policy is really important in terms of what flexibility is left over for optimizing our hydro assets for power generation. And really the six major categories in terms of what we're looking at when we're managing our river system is flood damage reduction, power generation, navigation, water supply, recreation, water quality. And of course, there's other factors that go into that, but those are kind of the six main categories. And so I mentioned that our hydropower is about 9% of our total portfolio, about 3,500 megawatts of conventional hydro. We have one pump storage facility as well, and we're considering building another pump storage as well. And Stuart's going to talk more later about pump storage valuation that we've been working with him on valuing that as a future asset. And so in TVA, all of our reservoirs are seasonal, so we don't have any multi-annual energy storage, but mainly what we're doing is we're raising the reservoirs up in the summer, and that's really for recreation, for water supply, for navigation, and then we're drawing down in the winter, and that's really for flood control is the primary purpose, and then our drier months are in the fall, so that fall drawdown also serves as water supply. Which kind of getting into that, we get about 65 inches of rainfall a year. And even though we're kind of equal on rainfall every month, the majority of the runoff is really in the winter months. And that's because we have less plant withdrawal evapotranspiration, which really takes a lot of that water out of the system during the summer months. So one of the things I talked about was flood damage reduction. We have a number of tributary reservoirs, which are the ones in blue that you see in that picture. And those are really our main storage reservoirs. And so we're storing water there, trying to keep it off of the main stem of the Tennessee for flood damage reduction. And one of the recent events, although TBA couldn't do a lot of it because it was more outside of our region, was Hurricane Helene last year. And that did a lot of damage to Asheville and that surrounding area. This is actually some drone footage from Holaschutz Dam, one of our reservoirs. This is after the peak because it was in the middle of the night. And it actually blew a hole in that powerhouse there. This is an old sedimented reservoir that's no longer used for power generation, and they since got rid of that powerhouse, but just reminds us of the power of flooding, and which is one of our primary objectives. Navigation, so the Tennessee River is navigable all the way from the Mississippi up to Knoxville, Tennessee, as well as we work the Cumberland River, which is manned by the Army Corps of Engineers, and that can go past Nashville as well. Water supply, definitely not water supply like out west. We don't have any of the water supply concerns that they do, but we manage minimum flows for about 700 water intakes throughout the valley, but not as difficult with the water concerns out west. Recreation is a huge part of what we manage the river for. The Tennessee Valley and area is really known for its lakes and lakes life and recreation and fishing. There's whitewater. So there's a lot that we do to manage recreation in the region. The University of Tennessee estimated it brings about $1 billion of economic benefit to the valley every year, which is something we like to pat ourselves in the back for. And then water quality. So we have a lot that we do for trying to maintain water quality in the river, whether it's we have liquid oxygen that we pump out in some of our reservoirs. We have aeration structures, auto venting turbines, and then other things in water quality is like temperature concerns. So TVA is a little bit unique in the sense that we can operate our river to help meet some of the temperature demands of our nuclear plants, especially. And especially Wheeler, which is downstream on the Tennessee River, gets really hot there. The water temperature can get 85, 88 degrees going into the nuclear plant, so like a warm bathtub. And so we have a lot of temperature concerns around there, and we have 3D models that we use to analyze the temperatures to help meet the permitting needs of how much we can increase the water temperature there. You can see in this here, you can see the outflow from Wheeler Reservoir in that picture, and then the intake is right there. One of the interesting things about Wheeler, because the intake and outflow are so close, if we're peaking in the summer, you can actually get like a sloshing effect where the water will hit the downstream edge of the reservoir and slosh back, and you can get that warm water going back into the intake. So one of the things that we do with hydro is try to maintain some steady flow during certain times in the summer, which also limits how much we can do peaking to meet our demand for other things. So one of the constraints on how we manage the power for the hydro system as well. So just talking about all of this, you can see a lot of these challenges, if you want flood control, water quality, thermal compliance, those all want low reservoir levels, whereas like navigation, recreation, all want high level water levels. So it's just a matter of balancing all these different objectives in terms of how we manage the system. So I'm going to get into a little bit more technical nitty gritty now about how we do the optimization of our hydropower. There's a lot that goes into that, but I'm just going to specifically talk about how we integrate with our production cost model. And so one of the primary tools that we use is a program called Riverware, which is really where we're turning our water constraints into goal programming. And we have a couple of different models there. We have one that goes out that 2-week frame for that midterm, and then an hourly one that goes out 3 days. And so we've been developing some new methods for how we integrate with our production cost model. Traditionally, the way that we did optimization for these models was more of an incremental cost or a incremental cost to depth. But that has been going away with some of our newer production cost models. Specifically, we're moving towards the portfolio optimization model from ABB. And so we've come up with a new method. And I guess one of the things I should mention first here is, TVA is not in a market, so we're a little bit unique in that sense. We're our own balancing authority, so we don't have market concerns, but we're trying to really use hydro to offset either our more expensive units or purchases off other markets from our surrounding region. So it's really about, how can we optimize that hydro field that we have, which is free, to offset more expensive costs. And so when we're optimizing these two systems, a little bit what I talked about with all of the constraints in hydro, there's a lot that goes into managing all of those constraints in the hydro system that are not practical to put in that production cost model. And so having all of that in one model, although ideal, was not really feasible. And so we've taken more of a decomposition where we're passing those constraints between these two models to try to get as close to possible to a co-optimization between our production cost model and our hydro assets, which and so the approach that we've taken is really we run a Riverware model that is an optimization model that comes up with really the constraints of our hydropower system. And so that gives us hourly min-max generation, daily min-max generation, and a 10-day target. And this is passing to the production cost model as a single unit. So it's really simplifying the solution, saying all of our hydro is just a single unit in the production cost model. And whereas we have over 100 different generating units in our hydro. And then we run that production cost model, and it comes back and it gives us an idealized hydropower solution for this is what would be ideal in our system for running hydropower over the next 10 days. And then we ingest that back into those other subsequent models in our Riverware as an optimization goal. So just a little bit of a diagram here to help wrap your head around that. We have a lot of physical modeling that goes into our hydropower system, whether it's modeling inflows, our hydrology into our system. That's where we're using a lot of similar tools to everyone else that was talked about yesterday. We're starting to look at AI weather forecasts. We're starting to look at AI inflows, and a lot goes into all that modeling for how we model our hydropower assets. All of that data goes into these decision-making models, the riverware. Those hydropower constraints then go into that production cost model, which gives us back that idealized hydropower schedule that then goes into our short-term and our midterm riverware models. And that short-term model is really what comes up with our schedule for the next day as far as hydropower, and then a preliminary one for day 3. So we actually do this twice. We do an idealized one with as most flexibility as possible, and then a more realistic one, and try to be between those two. So you can kind of think about the optimization here is we have all of these constraints on our system, and really what they're doing is shrinking the optimization space. All those other demands, whether it's flood control, water quality, they really limit the amount of flexibility that we have in hydropower. And so whatever flexibility is left in that optimization space is what we're using to try to optimize that hydropower generation for the rest of our assets. So that's been working really well. We're actually just moving towards this new portfolio optimization model. We'll also probably integrate with some new GE tools that we're using. And so that it's a kind of a unique method that we're using for this hydropower optimization. And we have, there's some potential enhancements. We can get more data into our production cost model to get more realistic things like ramping constraints. I think where we're moving towards is we're mostly optimizing our hydropower on that 2-week period where we can like move water around for a big event, or on that day ahead. And I think as we integrate more renewables into our system, we're going to get pushed more in hydropower to have more real-time flexibility. We do have real-time flexibility, but most of it's, the balancing authority will call up and say, what can you give me right now? Or what can you turn off right now during turn down situation? So having a more programmatic way for that real-time flexibility is also a challenge, and something that we're moving towards as well. Yep, that's it. Thank you.
Got a little lazy there for a second. But thank you, Gabe, for a really compelling look into TVA's hydro operations and how optimizing tools navigate real world constraints. So that operational ground gives us a really good starting point for the rest of our panel speakers. Next, we'll hear from Stuart Cohen at NREL, who will bring a planning and modeling lens to the conversation, with a focus on valuation of pumped storage hydropower.
Great. So thanks everyone for being here. So I'm going to give a pretty broad overview of a lot of things that we have going on in the pumped hydro space. So for those less familiar, I'll start with just kind of a why pump storage. Why are we thinking about pump storage valuation? Introduce you to a lot of the things that we're doing at NREL on the data and tool side to help with these questions. And then I'll get into specifically how we're using some of those with TVA. So it'll be good follow up from what Gabe was talking about. So first off, why are we looking at pump storage? So if you're less familiar with this technology, it's a proven long duration storage technology. In the US today, we have about 22 gigawatts. And while, batteries are certainly making really rapid inroads in the capacity space, from an energy perspective, pumped hydro is still, well over 90% of the energy storage capacity that's in this country. And so, today it's the only really widely deployed long duration storage technology from an energy perspective at the utility scale. And if you're unfamiliar, there's actually a lot of kind of action, at least in the licensing and permitting space around pump storage in the US. The development pipeline has around 100 gigawatts in some stage of the process. There's only, a very small portion of that is in the detailed planning stage. But what's also good to put into perspective is that globally, there's a lot of action in this space. So 50 gigawatts is currently under construction. A lot of that is in, like China and those countries, but also in Europe, India. And so there's a lot of global demand for looking at these long storage energy solutions. And that's one of the reasons why in the US, we're thinking about, okay, well, what is, a way to advance our understanding of the value proposition to serve the needs of the future. And so the reason for thinking about pump storage, and I already saw a similar table as this, is that, it can really provide this full range of grid services, all the way from, your bulk capacity energy services, all the way down to short-term stability, frequency stability, voltage control, and even, system restoration, black start. And so it definitely depends on the facility, because oftentimes, these are hydropower facilities that are integrated into river systems. But in general, these units can ramp really fast, switch relatively fast, maybe not quite as fast as lithium-ion batteries, but you have a lot of flexibility just with the system designs. Today, all of the pumps in the United States are fixed speed pumps. So that does have some limitations in flexibility, especially when you're in pumping mode. So they're either really at a given pump is either at 0 or 100%. So that certainly limits a lot of the regulation and stability services it can provide in pump mode. But a lot of the conversations around the new proposed facilities are actually around variable speed units. And that's so that you can get this full range of grid services, both in pumping and generation mode. And so like I mentioned, and has already been discussed, one of the key challenges in this space is valuation. And so I have one slide to kind of introduce you to what the labs in Deyoe are doing in particular to think about this space. And that has to do with this effort called the Hydropower Vision Roadmap. So we put out a study way back in 2016 looking at kind of a future vision for the hydropower industry. And the labs are continually working with industry around framing sort of what could achieve that vision and what actions should take place across the industry to meet those goals. And so, since this is kind of a new audience for me and talking about this hydropower space, I just wanted to introduce you all, because I think that one of the set of stakeholder groups that might be less represented are sort of the more broader power sector community. And so we have, in particular, have a specific area looking at improved valuation that's focusing on recognizing the value of different services, understanding how to compensate them, and then how to translate that into financing support. And I think that's, honestly, a really consistent discussion across a lot of the long duration storage technologies and a lot of technologies that provide these flexibility services. And so I'm very interested kind of throughout the rest of this meeting to talk to you all about this space. So next is kind of what are we doing at NREL and other labs to think about pump storage. So at NREL, we're doing a lot of data development, both on the resource assessment side and cost assessment side. And so similar to what you're all probably already familiar with, our wind and solar resource assessments, we now have a detailed site-specific pump storage hydropower resource assessment that we've been doing for a few years now. So that's another geospatial analysis looking at topography, hydrology, different environmental exclusions, and so on. And right now it includes closed loop sites, which would mean a site that does not interact with a river system. That's one way to think about mitigating environmental considerations. But we also have sites that you can add on to existing reservoirs to reduce the need for construction. And also we've looked at mine pit opportunities as well. And so we have an interactive web tool to look at this. I meant to bring one to the stage, but I have a bunch of postcards with QR codes if you're interested in physical materials on any of this stuff. And so that's a good way to kind of explore that. And just to put it in perspective, I mean, this is a technical potential, not an economic potential, but if you add everything up, I mean, it's like 80 terawatts of capacity. So there's a lot out there to consider in this space. Built into that is a cost model. And so we've worked with industry folks, engineering, procurement, construction firms, using a lot of the information that's available from an EPRI design guide, and built an actual bottom-up cost model to look at pump storage as well. And so that's another way that we're trying to put, publicly available open tools out there for people to think about this technology and how it, fits into their portfolio and their considerations. And so right now we have a downloadable spreadsheet, but we're actually working on an interactive web tool to use to work with that as well. And then kind of bringing this more towards what's probably more to the bread and butter of people in this room is sort of how does that feed into the power system models? So I'm not going to go through everything, but this slide is just kind of giving an example workflow that at NREL we use for a lot of our studies, where we kind of go from where we go one way and sometimes iterate between capacity expansion, long-term planning models, feeding those future infrastructures into production cost models, looking at resource adequacy, maybe even nodally downscaling those to run in power flow models and look at short-term static and dynamic stability, and to try to create, a fully integrated system modeling approach to understand, what the future could look like. And so just kind of the point I want to make in this context is that, on the pump storage side, we're developing data and tools all the way from this, kind of resource assessment, cost modeling, all the way down to like dynamic models for variable speed pump storage systems to be able to look at all these space. So one example of how we're doing that is with TVA. And so the Department of Energy, actually, the Water Power Technologies Office funded this work, and they funded a lot of projects looking at pump storage valuation. Todd from Argonne is here. They do a lot of that work. And so this is just one example of that. And so the idea here is that we're working with TVA to help them understand the value proposition for a potential new pump storage because of the challenges. I mean, these are multi-billion-dollar investments, right? And so it's one thing to finance, a small 2-hour battery that's very modular and you can kind of stack and go over time versus, hey, we want to invest $4 or $5 billion in a new dam. So it's a different discussion with a bank, I guess I would say. And so this is a challenge. And so the idea here is to kind of bring in some of the more research-oriented tools that are forward-looking and thinking about different ways to represent long duration storage and other parts of the power system and see how that kind of influences the discussion around valuation. And so we really did two things in this effort. One was to kind of do a deep dive and digging into looking at their modeling approaches and think about ways in which that could be, tinkered with, I guess, and improved and expanded upon. But the other thing was to do some parallel modeling and analysis ourselves. And yeah, I mentioned this is from Water Power Technology Office. So I'm going to focus on number 2 here, kind of in interest of time. So what we're doing in this study, really, it's a collaboration between NREL, Argonne National Lab, and Pacific Northwest National Lab. So PNL is focused on kind of the hydropower side. Argonne is working with this pump storage evaluation toolkit, which is more of a screening level valuation analysis. And then at NREL, we're kind of doing the rest of the stuff. So we have our REEDS capacity expansion model that's currently fully integrated and iterates with the resource adequacy model, PRAS. And then we're taking those solutions, downscaling those into our Plexos production cost models. And then on the side, in parallel, doing some power flow and stability modeling. So I'm just going to briefly go through just sort of some of the preliminary findings that we're exploring in this space. It's we're not quite to the point of giving like the cost numbers and the actual value assessments, but just want to give everyone a flavor of how we're looking at this. So the first thing on the capacity expansion modeling side is to look at a range of portfolios, and so we've worked very closely with TVA. Also thinking about, what they're already looking at in their IRP procedures. And we're defining different scenarios to try to get a range of technology mixes for the future. And so this on the figure is showing the 2050 capacity mixes and generation mixes in TVA for just a few of the scenarios we're exploring, just to show you the range of how we're tinkering with, fuel prices, technology costs, even kind of deployment limits and considerations on variable renewables to look at these futures. And so, for example, the scenarios, at least as shown on this figure, are looking at a range of 20 to 47 gigawatts of solar in 2050, We're actually trying to get an even lower solar just to get a bigger range there, because then that balances out with, what happens in the natural gas space, even scenarios for, what if there was some new nuclear deployment, small modular reactors, something like that, and so on. Because the reason for this is because this generation mix is going to influence the value proposition for that pump storage unit. And so, for example, if you look at those 4 scenarios, kind of with and without this proposed new pump storage unit, I'll apologize, the colors on here are challenging because the pumped hydro looks a lot like the 8-hour battery. But basically on the positive side, you're going to see pumped hydro and maybe some other stuff. And on the negative side, it's going to be whatever wasn't built because that pump storage showed up on the system. And so again, this is preliminary. I'm not going to make any strong conclusions about what's going on here. But the idea is that in these different scenarios, these different grid mixes affect what the pump storage might displace. And so generally, it's probably obvious to people in this room, they're going to compete and displace with other flexible technologies, batteries, and natural gas. But the extent to which it does that and which technology it does that with depends on the scenario. And we also see some complementing of things like solar and even a little bit, in this case, nuclear, which is kind of interesting. And so again, that's just to say that changes in infrastructure, determine the impacts of pump storage on not only the investments, but also ultimately the costs as well. And so eventually we're going to be looking at the cost implications of this and using that to inform some detailed financial analysis that Argonne is going to do. On the production cost side, this is even earlier stage. So I just wanted to kind of show some examples of what's going on. But we're taking these planning model solutions, running them in 8760 dispatch simulations to understand kind of how this new pump storage would operate. One of the known operating challenges in a lot of regions is that we built these pump storage systems in the 70s to complement nuclear, and we knew they were going to pump at night and run during the peak loads in the day. Well, now with all the solar, that's completely flipped, right? And so there's a lot of questions and considerations around when are you going to pump. Now we're thinking about pumping at the nominal gross peak load condition, which can create stability considerations. And so those are the types of things that we're starting to dig into with these operations models. And so, you can see how in this example, the pump storage is generally outputting electricity in the evening hours, early evening. And so we're going to be looking at, the cost implications of this in addition to things like unserved energy, curtailment, and so on. And then this is just an example of what we're doing in the short-term stability space. We're using PSSC models that TVA has provided us with and looking at things like the voltage support capabilities, inertia response, troop response. I'm a mechanical, not an electrical engineer, so this gets further from my area, but we're doing a lot of simulations looking at kind of the grid strength and stability implications of this new pump storage unit. So that's kind of what I cobbled together to present to you all today. The key things that I really just wanted to leave everyone with is that, I think most people will understand that pump storage is an established storage solution, but it does have a lot of potential for the future. And so understanding how the valuation, compensation, conversation today is really important because it's different than when we built these in this country anyway in the first place. NREL is creating a lot of data tools. Other labs are doing this as well to help inform this conversation. So really just kind of want to help raise awareness of all of that. And we think that, a lot of the capabilities and tools that we're building on the lab side can really do a good job complementing what's happening on the commercial and utility side to have this discussion. So that is all I have. And this is all.
All right, thanks, Stuart. That was an amazing presentation and a clear reminder that even established long duration energy storage assets like pumped hydro can be undervalued if our tools and operational models aren't designed to fully recognize their contribution across different services and different scenarios. So thank you for that. Next up, we will be building on that with Donny Holaschutz from inodú, who is going to talk about how we accredit resources in the first place, before which I think we just have a little bit of a slide switch. Yeah.
Well, sorry, I had to be the guy that, brought the PDF presentation. We use custom fonts, so I didn't want the presentation to look terrible. Sorry about that. Well, thank you very much for accommodating that. Sorry, my throat's a little coarse. So I'll be talking just in more general terms, like some of the challenges assessing the contribution accreditation of long duration energy storage for resource adequacy. And I'll discuss some challenges in different markets. We'll look a little bit at CAISO, essentially how the system's behaving there. We'll also look at some of the challenges around ERCOT. So in the agenda today, it's going to be divided into 5 parts. First, I'm just going to show how exciting it is with short duration energy storage, how the markets are growing in terms of the adoption rates in wholesale electricity markets. Then I'm going to do an overview of some of the challenges and try to frame the problem around resource adequacy contribution accreditation and where I see some of the challenges with the way that we do modeling, how we think about that. And it's going to complement some of the stuff that the panel has already discussed. And then I'm going to deep dive into one specific challenge, which is essentially we need to look at a broader temporal perspective, right, to understand the resource adequacy needs of the system and really, determine the value of assets like long duration energy storage. And then I'm also going to talk about how to connect the adequacy needs of the system with the functions and attributes of resources, essentially, and how to look at that. And I'll go through some conclusions and questions for the ESA community. So we're a consulting company, and these are some of our clients, and we've done work in North, Central, South America, and work with a lot of developers of energy storage, and a lot of different types of utilities clients and that kind of stuff. We could talk about that later. So what's exciting is if we look at the markets and we look at short duration energy storage, we see that these graphs are growing exponentially. If we look at some of the markets, the wholesale markets that are leading the adoption, we have ERCOT and CAISO really growing. IMO in Australia, NISO in the UK have really adopted technologies, but we have some markets like we do a lot of work in Chile, and there's a big amount of adoption happening as well. Most of the adoption in these wholesale markets have been for shorter duration batteries between 2 and 5 hours. If you're interested in this, we do a monthly newsletter where we update these values essentially. But so come and see me, and happy to share that with you. So basically, we can see the existing capacity in the different markets. CAISO and ERCOT are growing. ERCOT added about 5 gigawatts last year. But what is interesting, we see a lot of development in the pipeline as well, right? These are on the right-hand side, we see all the energy storage assets with an interconnection agreement that it's set to be developed by 2026 or being reported that way. So there's a lot happening in the market, but not a lot with long duration energy storage besides pump storage. Essentially, it's something that is emerging. New technologies are emerging, right? So I'm going to talk a little bit now about the overview of some of the challenge to assess resource adequacy and capacity contribution accreditation. So if we look at CAISO, for example, I'm going to go through the definition. This comes from the CAISO tariff, so we're all on the same page. What does net qualifying capacity mean? And I mean, this definition is kind of redundant, but that's what the tariff says, right? Qualifying capacity is a maximum resource adequacy capacity that a resource adequate resource may be eligible to provide. That's what the tariff says. And it says net qualifying capacity considers a reduction from testing, performance, and deliverability limits. Whether or not that is happening, that's a question. And every year there's a deliverability study that is focused on peak demand to determine how much capacity is available for resource adequacy. And so if we look at the graph on the left side, we basically stack the NQCs of all the different technologies, and we show the 5 days of maximum load in 2024, essentially. And we show the load, which is what's published, and an estimate of the load plus behind the meter generation. And so we start seeing some challenges here, right? We see that solar is accredited for the night, right? So that's a challenge, right? Is it really contributing during the night, right? Or it has NQC during the night. Is that really happening? Storage is basically accredited 24/7. And there's issues with all these other technologies. And if we look at in the bottom graph, we look at the real generation of batteries and the NQC, we see that storage really doesn't reach the maximum dispatch and it reaches its NQC levels. But CAISO does publish operational reports, and it says on July 24th, which was a period of high demand, essentially, batteries did provide adequacy, or they did meet those levels because they were providing ancillary services. They were not dispatched, but they were providing ancillary services, and they bid into the market, but they were out of merit order, so that the capacity was available. But this raises a question, right? What happens during other periods that are non-peak, essentially, right? Is one value for a monthly accreditation the right way to go? And this starts going, showing a challenge. And I think this challenge has been detected. Yesterday there was a great resource adequacy group that was talking about some of the challenges and trying to look at addressing seasonality in capacity markets. CAISO and the CPUC are going through this process as well. And there's something going on in the market. And I don't know if you guys are familiar with the CPUC slice of day, but that's a new approach in terms of accreditation that they're looking at. And they want to look at the contribution of the different resources through the 24-hour period, essentially, and trying to understand that. And whenever you look at the history of how that came about, they said, hey, there's something going on. We need to change this resource adequacy framework. And they basically early on said a couple principles of why they want to do it, right? They want to make sure that, they're actually balancing the grid and minimizing costs. They're also addressing the hourly sufficiency, reliable operations, and they're also meeting the environmental goals. They're balancing the granularity and precision and meeting the hourly resource needs. So this idea of like temporality, we need to meet the needs of the system, throughout the year, hour by hour, essentially. And we want to do it in a simple way. There's something going on that's, complex about it in the way that we're doing it today. We also want to make it transactable. We want to make sure that, we are able to do it in a durable and adaptable way in the energy transition and the grid that is changing. So I basically summarize and say, hey, the markets are telling us that we have a need for simplicity, right? Whenever we do accreditation and we look at how that is done, we really need to align it to the system reliability needs, right? When are the most critical times, and the resources, are they really going to be available during those times, right? We also need to ensure that, we're supplying, the requirements of the system in terms of resources adequacy on an hourly temporal basis, so a broader temporal basis. And we're ensuring minimal cost, environmental goals, and the reliability needs, right? So ESIG has published a couple guides on resource adequacy, and I grabbed some little nuggets from the guides that I think are important, that are talking about some of the needs to look at how we do resource adequacy, and take a broader perspective, so we can align the system, the system needs, and really actually have the resources that will, be able to be there for all these envisioned future operations. So one thing that, one of the nuggets from the guide says, early tools evaluated only single peak load periods and did not assess risk of shortfalls across the entire year. So really going across, like, we need to think about resource adequacy from a more temporal perspective, a broader perspective. Establishing the appropriate level of power system adequacy requires the collective judgment of planners, regulators, and customers and other stakeholders. And that goes to my figure in the right. Essentially, whenever we think about resource adequacy, we need to think about how we balance these other drivers to be able to meet the expectations of the system and the reliability. But it's not only reliability, we also have to make sure that we're taking on the same risk, we're ensuring the right performance, we're meeting the stakeholders' needs, and we're communicating to them. So, two things that are relevant in terms of the perspective that we need to address is, obviously, we need to address these system needs in a robust range of potential operational environments, right? We really need to think about how the system is going to operate and expand our views, right? And we also need to do it on a broader temporal basis, essentially. And what do I mean by a broader temporal basis? We need to think about the critical periods of the system from an instantaneous perspective all the way through like a yearly perspective. Our traditional focus has really been making sure that we have enough hourly energy and capacity. We meet the hourly and energy capacity constraints during peak hours. But if we're going to want to uncover the value of long duration energy storage, we need to look beyond that. We need to look at the non-peak hours. We need to look at the days with supply constraints, because sometimes it's not a capacity constraint, it's an energy constraint in the system with renewables. We need to look at the seasonal supply constraint. And we also need to look at the instantaneous. And I'm going to focus on points 3, 4, and 5 later on to give some examples. But actually, number 1, Stu was talking about that in terms of how pump storage can provide those services. And that's actually quite important as well. Traditionally, whenever we're looking at resource adequacy evaluations, this is a figure I drew to try to organize. We're really focused on whenever there's resource adequacy, accreditation, and evaluation and determining the contribution. Basically, we're very focused on these like stochastic risk methods, which are important, right? We basically are expanding our view on adequacy metrics and target, which is important, which is going to expand the way that we look at risk. And in some other places, we don't even use these stochastic methods. In some other markets around the world, there's more historical and heuristics and just performance during critical times, essentially, right? And this is sort of the methodology that's sort of developed over time. But I think one thing that we need to do is think about how to broaden this, not only through the temporal perspective, but also basically be able to do conceptual analysis, right, to ensure that we have a resource adequacy system, a system that meets the goals, needs, and envisioned operational environments, right? And these risk assessments do not really cover all the envisioned potential environments that are going to happen in the future. So we need to broaden the way that we need to look at that. And for that, we need more tools. And we also need validation. And I'm going to go through the concept of validation and why it's important. I'm a systems guy. I love systems thinking. I went to grad school for that. So I kind of bringing back some of grad school notes and some stuff from the International Council on Systems Engineering. What is validation? Validation is a process in which we go by to make sure that we're meeting the system needs and the system goals. But we're also going through a process where we're putting, the concept that we're developing, which is its function and form, or the architecture of the resource adequate system, through very different envisioned operational environments. And we're trying to make sure in this process of validation that we're meeting the system goals and needs through this broader perspective. And so whenever I, try to summarize in how we do resource adequacy, essentially, what we need to do is we need to expand our approach. And basically, we need to have an approach that whenever we're doing modeling and we're doing assessments, we're thinking about the system needs, we're thinking about the system's goals, we're developing, concepts for resource adequate electricity system, and we're doing analysis on the concepts that we're producing through production cost analysis, historical analysis, reliability modeling, real-time modeling, and we're doing this assessment across a broad spectrum of temporal basis. So we're making sure that we're covering the critical issues that are happening in the very short term, which is really leading to some, for example, the blackout in Chile that was recent with high integration of renewable really had to do with really issues around the short term. But also we're uncovering some of those issues that are, daily and seasonal and yearly, and we're doing that type of assessment as well. And we're also doing this stochastic risk analysis whenever we're thinking about envisioned use in operations, but we're complementing with the other, with other types of analysis, and we're going through this validation process essentially. So I'm going to dive a little bit deeper into why it's important to adopt a broader temporal perspective to basically assess the value of long duration energy storage. So I'm going to focus on these 3 points essentially, which is the value outside the peak hours, essentially the daily supply, the day supply constraint, essentially, and the seasonal supply constraint. So whenever we look at the, off-peak constraints, essentially, so what we did here is we ran a production cost model, essentially, for using the IRP's assumptions, the preferred system plan in the CPUC's 2022 to 2023 IRP. And this graph, this is hard to understand, but what we have is the 24 hours of the day. And what we have in that line on the top is the hours, the top 5 days of maximum load for each hour of the day, essentially. And then in the bottom, we have how much the short duration energy storage capacity, how much remaining capacity they had, and how much they dispatch. And what I mean by remaining capacity is, the amount of energy that they had stored and how much capacity they had available to actually give to the market. And this is done through a day ahead type production cost model, and it doesn't show the real-time deviations that could happen and what could really go wrong. But what it shows us is that, short duration energy storage after 10 p.m., they really don't, contribute a lot to the system. They basically contribute with less of their capacity during those hours of maximum load. Essentially, that's what this is showing us. And whenever we looked at this further, we see actually that whenever we run these production cost models, the reserve margins that are being defined are actually not being met, during the night. Essentially, there's challenges. They're much lower that they're actually being said to be through this stochastic production, a stochastic risk analysis, essentially. Another challenge here that I'm going to show is the seasonal variability and the challenge of seasonal variability. And to show this, what we show in the two graphs, essentially, the top graph shows the daily production of renewables and daily load, essentially, in ERCOT. And then the bottom, we showed the manageable generation capacity, the daily production, and the load as well. And so what we see, if we look at, point one, essentially, we see that in 2024, there was a period in ERCOT where actually the demand spiked significantly, right? And we had to rely on a lot of, gas generation to supply that demand. And we had wind resources that, really dropped on a daily basis very significantly, right? So whenever we're looking at the value and uncovering the value of long duration energy storage, we need to think about how long duration energy storage is going to be able to contribute during these events, right? And how it's going to be accredited to be able to contribute during those events. We also see in point two, in number two, and a lot of details are written, but you don't have to read them, but essentially there was a day when there was high demand as well, where wind production dropped very significantly. So we need to think about how we're going to address that. And what is causing this? What we show here is the daily consumption in Houston and its surrounding against the daily consumption against the average daily temperature. So it's a very strong correlation. So what we see is that in 2022 and 2024, there were significant days where the temperature in these cities led to so much more demand, right? So much need for space heating, essentially. And these extremely cold days are actually uncoupled, or they're actually happening when the resource mix might be constrained, right? Where we have these drops of solar and wind generation. Another challenge that we want to showcase is this issue of seasonal constraints, right, in the system. And the example here is CAISO. So what we see in CAISO here, again, we have the daily production and the daily demand and the daily manageable generation for 2022. And we see that the daily production of wind and solar basically in the worst winter day drops by 81%. So how are we going to charge batteries whenever, or what resources are we going to need to replace all that gas and all those imports that supply demand? That's the type of questions that we need to be answering and looking at whenever we're looking at contribution and accreditation, essentially. So when we talk about some of the, the challenges, there's another challenge, right? How do we connect system adequacy needs with the functions and attributes of, the different assets in a technology agnostic way? So if we think about traditional resource adequacy accreditation, right, it's been, kind of limited in many ways, and it's evolving and it's different in different markets, but it's been limited to assessing the power supply contribution, right, of an asset with a limited 4 to 5 hour supply guarantee, right? And the question is this valid during the energy transition? So what I show here is the function of an energy storage facility, right? So the functions of an energy storage facility. So you first need the supply, the energy, right, that you're going to use to charge the battery. You're going to store the energy. Then you have available capacity, right? And then the capacity is going to respond and provide those services. And then the capacity is going to dispatch and actually in a certain amount of time is going to be able to provide those services. And it has to be do it in this broad temporal basis, essentially. So we need to, there's like power supply, delivery, energy reserves, and energy supply. And when we map that to the system needs, essentially, and we focus on the longer duration stuff, we see that, in the longer duration issues, which is meeting the seasonal constraints and the yearly constraints, it becomes very important to think about the attributes associated to like energy reserves and energy supply. And especially, we need to think about what attributes we need to look at from an energy reserves and energy supply perspective to value the contribution of long duration energy storage. And so I'm going to look at, show you a little bit of an example really quickly of in the energy reserves, right, in the stored energy, how, the operations and whenever we run production cost modeling, how does the value of the stored energy change really what the assets are able to contribute? How does the availability of the stored energy, change essentially how much long duration energy storage is able to contribute? So basically we ran 3 sensitivities, again, for the CPUC's IRP, essentially 2022, using the assumptions of scenarios. And the IRP and developed by the CPUC, they install a 500 megawatts of compressed air energy storage, essentially. So we use those assumptions. And we did 3 sensitivities on essentially operational state of charge policies, right, to address this issue around energy availability and value of energy to provide adequacy to the system. And the first sensitivity we ran, we said, okay, let's keep the compressed energy asset to be able to operate however economically most efficient between 10 and 100%. Then we had another sensitivity where we limited, we said, hey, by the end of the week, you should reach 50% essentially. And the sensitivity 3, we said, we need to keep a certain level of stored energy so we could provide adequacy to the system and see how that impacts essentially, right? So whenever we look at the results of the most flexible energy use, economic use, which is sensitivity 1, here we have, 5 kind of different things going on. So the first is the average renewable energy generation for 2032 essentially, and the average demand. Then we have the spot prices, the average spot prices in the different regions. We have the charge and discharge of the compressed air energy facility. We have the charge and discharge of the short duration energy facilities. And then we have the state of charge of the compressed air energy facility and short duration. So what we see here is that the compressed air energy facility, in an economic manner, it really, if you don't set any requirements of how much energy availability should be or stored energy availability, its tendency will be not to charge because the differentials are not high enough, essentially. And, the efficiency of the battery leads it to say, hey, I don't, want to be charging and discharging because it doesn't make sense from an energy market participation. This is not taken into consideration, this is a day ahead type planning production cost model exercise. What we do see is with the shorter duration batteries, those, have a very, consistent state of charge, but that's not the case with the oh yeah, thank you very much. I appreciate it. Yeah, we don't have that challenge with the short duration energy storage. We do have it with the long duration energy storage, right? So essentially the question is, what requirements are we going to set for energy availability in order to have enough state of charge so these assets are able to contribute in the market and provide adequacy? And here we show another example, essentially, where we show actually some of the days with maximum demand and what happens with the three different policies, essentially. So we see that whenever we don't prescribe an energy availability of state of charge policy, essentially what we have is that during the periods where the spot prices are not, there's not very high differentials, the model really, I mean, essentially the battery doesn't keep a charge, right? But in the third sensitivity we prescribe, there is more state of charge in the battery, right? But that's more expensive to do that because you're charging under non-economical conditions, but you're able to provide adequacy for those days where the energy supply is much low and the demand is very high, essentially. So I'll just go briefly through the conclusions. I'm already a little bit over. So I think it's important to really expand on how we do resource adequacy evaluation to uncover how long duration energy storage contributes and also how it's accredited. I think looking at this broad temporal perspective is very important. I think it's also important to do conceptual analysis to really think about and use other tools prior to doing stochastic risk methods, because the stochastic risk methods do not tell the whole story, essentially. So we need to explore what are the concepts that are really going to get us to a reliable and adequate system. We also need a broader range of tools. We need to establish a validation process as well. The validation process needs to ensure that we meet the system needs, essentially, and the stakeholder needs through a broader set of operational scenarios. And then we also need to define the attributes of these technologies in a technology agnostic ways and see how those actually match up against the system needs, essentially. And there's some questions that I'll leave there. That's it.
Thank you, Donny, for that very insightful presentation on creating a more effective accreditation framework for LDES assets. I'm sure we're going to have a very robust discussion at the end of this panel. Last but not least, to close out our presentations, we turn to Ryan Deyoe from Telos Energy, who will walk us through some real-world modeling and policy engagement in Hawaii. So Ryan.
Okay, hey everybody. Thanks all for the great panel session so far. I'm Ryan Deyoe with Telos Energy, and I'll be talking to you all about a very specific island system in Hawaii. We're going to be talking about the Oahu system. We're going to be looking at how long duration energy storage, specifically multi-day energy storage, 100-hour batteries is kind of what we're looking at, and how that provides firm capacity value or firm energy value, if you want to talk about it that way, in Hawaii in high renewable energy penetration levels. So before I get going, this work is in collaboration with our client, the Hawaii Natural Energy Institute. Thankfully, with our partnership with them, we get to do a lot of really novel studies around high renewable energy systems and tackling some of the challenges for island systems. Also, apologies, I am battling a light cough, so I might cough intermittently. In case you're not familiar with the Hawaii grids, we're looking at 6 isolated grids. We've got all these individual islands that are not connected with each other, so they each have their own individual challenges. One thing I want to stress in this presentation that I'm sharing with you today is that because we're looking at island systems, their risks develop differently than you might have on the mainland or like a larger interconnected system. So they're really outage driven based on their existing thermal capacity or other resources that they have. As you can see, each island is rather unique in terms of what renewable energy resources they have available to them. All of them have some form of solar, quite a lot of rooftop solar. Some of them have hydro, geothermal on the big island, Hawaii Island. You might all be familiar with that. We're going to be specifically looking at Oahu, which is the most populated island, has the highest load, and also is fairly land constrained, both due to population and just its size relative to an island like the Big Island, hence its name. So we're looking at Oahu. They're around 30% in their RPS target. Going forward, they have goals, all of Hawaii has goals to be net zero by 2045. So their RPS is going higher and higher as time goes on. And one of the important things about Hawaii is that they also have an extremely old existing oil fleet. So some of these units in Oahu and on the other islands are there from World War II era. So these assets are increasingly old, and they have an increasingly stressful operating regime due to the changing resource mix and just reduced parts availability, critical maintenance periods. And as I mentioned before, when these units go on outage, they do drive loss of load risk, rather than, if you think about the mainland, their loss of load risk is being driven by outages, but it's also being driven by extreme heat, extreme cold, and other dynamics. Whereas like individual units on a small system, it's about 1,200 megawatts of peak load, really drives that risk. These charts show the weighted forced outage factor of the steam oil fleet over the past, I guess, almost 20 years. And you can see this really sharp increase kind of prompting both our analysis and some of the upcoming resource procurements that Hawaii is trying to facilitate in the next few years, both for renewable resources like solar and storage, as well as for new firm capacity resources, new combustion turbines, stuff like that. So that's causing a reliability challenge. There are a lot of plans to get solar and storage on the system, and they will contribute to reliability. They will allow retiring some of these aged units. They've already retired the coal plant in Hawaii on Oahu, and they've retired two of the steam oil units. So they're on their way, but they can only retire so much with solar, short duration battery storage. There's other resources available, but wind is a bit challenging to site in Hawaii. So that prompts our analysis, which is, let's look at an alternative to firm capacity or alternative to fuel-based capacity, right? Oil capacity units. We want to look at how can we enable more oil capacity retirements on an aging and islanded fleet using long duration energy storage. As I mentioned, this is multi-day energy storage, 100 hours. So not quite a week, but a lot longer than the 4-hour batteries that are currently being built on the island today. It's a mixture of like between 4 and 5 hours. One thing I want to stress is that we're also looking at how new oil capacity, new oil CTs, maybe they could be converted to biodiesel, or maybe they can be converted to some other type of low carbon or zero carbon fuel. We're also going to be looking at new firm capacity resources just as a comparison point. There's a lot of reasons that folks in Hawaii want to not build new oil capacity. They'd like to reduce their dependency there. But it's important to look at both of those things when we're trying to compare. So our objective, evaluate firm capacity needs at increasing levels of solar and storage. Like I said, you can get some continued reliability with high solar and storage levels, but it does level off. Quantify how LDES can reduce the amount of firm capacity needed. We're going to compare between new firm capacity, new fuel-based capacity, combustion turbines, internal combustion engines against LDES. And then we're going to also talk about the modeling challenges. We've already had some of that hinted at today around, this long-term optimization for a resource that extends its duration beyond your day-ahead market or your couple-day period of optimization in these tools that we use. So we'll be talking a little bit about some of those specific challenges. So both portfolio analysis and just the modeling weeds. We've got other work coming down the line looking at optimal portfolios and cost comparisons, but really we're just trying to look at what's the reliability metrics and how can we just start there as the baseline. evaluated a lot of different scenarios in this study. This is not all of them, but this is like the key marks. We've got just the existing fleet. How much can we retire off of that while we just add solar and storage in increasing levels? We've got, which to set the stage, that is mainly what Hawaii is building, which is solar paired with 4-hour battery storage. There are some ideas and plans to build offshore wind on Oahu, but as we all know, that's a challenging prospect. So we're keeping it constrained with like what's getting added now and in the relatively near term. But we do push that up to a pretty high 70% RPS level towards the future to represent that long-term view. We're looking at 350 megawatts of firm capacity additions. This kind of fits along with recent proposals. So that's why we picked this 350 number. We're not evaluating anyone in particular. It's not like technology specific, but we're looking at generic thermal capacity at this size. Similar for 100-hour battery storage. And all these cases have the same rooftop solar. This is a projection based on current trends in rooftop PV. Within all that, we run our probabilistic resource adequacy analysis. We've got 25 years of solar data. We've got historical wind data that we don't have as many years for, but we have actual operating data that we roll over these different solar years. So it's not a perfect correlation between wind and solar, but we have good operational data. And we've got random generator outages on the existing units, which, as I mentioned, have some high outage factors. And then the new units are also getting those random outages. And we run, in this example, 520 simulations per case, so per storage level, per retirement level. And you'll see that illustrated in some charts later. We're probably running more samples in the future, but this is directional. We feel pretty good about showing just what's that starting point in terms of what reliability you can maintain. I think it was really great that some of our panelists, like Donny, mentioned that we need different resource adequacy metrics. That's something that we at Telos really strive to do. For brevity, I'm going to look at some of the most familiar ones, which is loss of load expectation in days per year. And I'll be also talking about ELCC a little bit towards the end. In this work for our client, we are looking at expected unserved energy, size, frequency, duration. So those things are important, but we don't have all day. Before I dive into the RA results, I think talking about scheduling long duration energy storage, particularly multi-day, at least in my experience, is challenging. And Donny alluded to this. Just to walk us through a simple example, this is our model with one sample, one draw of outages and weather. And we get this problem where without foresight beyond our 1 day or even a couple day dispatch, this is a 1 day look ahead. Without foresight or operating rules, this battery is low energy efficiency or low charging efficiency. So it just takes whatever the starting energy we gave it was and just draws it down and barely uses it again because it's not a valuable asset unless it can see further in the future. I mean, this is when we're talking about that forecasting that we've been talking about the past day and a half is really important for the actual operations. And we're looking at a small forecasting window, and we don't want to have it have too much perfect foresight. So we're going to assess different methods to balance realism, cost, and reliability. Right now, we're focused mainly on this reliability and realism without giving too much foresight. Later on, we'll be talking about, not here, but we're working on looking at the cost trade-offs of different operating regimes. So what we can do is we can give our battery, our model, that 1 day look ahead, and then we can give it a target. Say, hey, let's hit 70% state of charge and give it a penalty, right? So it's a soft constraint in your model. That does require a little bit of tuning for those that are familiar with these energy penalty targets. Thankfully, we can run a lot of simulations in Hawaii to sort of get that optimal value and then look further down the line at how that changes the cost of the system. But there's definitely a sweet spot in the Oahu system for what that price of energy should be in sort of in the tank of the battery. Either way, what it does is it reaches its state of charge and it sits there, but it doesn't ever go really above it. Some of those little squiggles are because we have a self-discharge. That's kind of the main problem here. We never get above it, so we still get unserved energy in some of these examples. We can then do a 70% state of charge target, but give it a decomposition, take that year, do some more aggregated analysis, not as granular, and then get a decomposition of storage targets. The problem is that that decomposition has a little bit too much information on what those outages look like. And we don't want that in a risk model. So we opt for the state of charge target with a penalty price. To illustrate this in a little bit of a different way, I like these charts. We've got our multi-day storage SOC. We've got a 1 week rolling average of solar, and then we've got one draw of thermal forced outages on this Oahu system. So you can see like we're at that state of charge target. We're drawing down maybe when we've got outages. We're drawing down when we've got low solar. And you can really see we've got this period. This is from one sample draw of a really intense or really low period of solar where we're drawing down that long duration battery. And we've got some thermal outages at the beginning, but we do have a loss of load event once that battery is drained. And so that's really the challenge we're trying to quantify is like, how often are you hitting these events where either the duration of the battery is the limiting factor, or maybe it discharges and then it has to recharge. And that's kind of what we illustrate here with another outage draw where we've got a different battery profile where it charges down, but then you've got some periods of additional forced outages that happen in your next model run where you're like, actually, we discharged all the way down and then we had another high outage event on this island system, and that gave us a loss of load event. So we did this analysis for each of these cases. It's 520 samples across an entire year. So this is where we started with. Now this is a big, maybe a bit of an eye chart, but these are our loss of load expectation results in days per year just for increasing solar plus 4-hour batteries. So you can see at these different RPS levels, we can enable a few hundred megawatts of existing oil capacity retirements. When we add 100-hour batteries using that state of charge target across these simulations, flip between this, you can see we enable about 361 megawatts at this first RPS level. And as you're going further down, that incremental retirement is about 250 megawatts of additional oil capacity that you could retire. And so this is important for Hawaii. Obviously, there's no 100-hour batteries currently deployed, certainly not at 350 megawatts of scale. But this is illustrative of some of the benefits that you might be able to receive instead of building maybe new firm capacity, new fuel-based capacity. I should be careful with my words. And so this is that comparison. Each of these lines, each of these dots on these lines represent the model at approximately 0.1 days per year loss of load expectation. That is not Hawaii's reliability criteria. It's actually a little bit better than the implied criteria they have. And it is, of course, only one dimension, but that's what we're looking at here. You can see that your ability to retire existing capacity, which is that y-axis, is better with those oil replacements, those new units that are more efficient and have lower outage rates. That makes sense. LDES is not too far off. So it's a promising alternative in this analysis to not build new oil capacity and still get further down that retirement track to get rid of some of those really, really old degraded units. If you don't add either of these options or an alternative, you really see this leveling off on your chart of how much you can retire as your RPS levels are increasing. I've showed you guys this chart, right? These different LOLE metrics. This is all based on that state of charge target and that 70% state of charge target and some decomposition. Excuse me. So we wanted to look at the sensitivity of your LOLE, your loss of load expectation metric, when you had these different targets. So I took the really high RPS level, the 3,000 gigawatt hours is like 70% solar or 70% renewable, a lot of solar and storage, and then ran them over the same cases, but with different state of charge targets and without the storage decomposition. So without that foresight into outages. And really what you see is you kind of get this trajectory of if you have a higher state of charge target, your trade-off on reliability, you know, maybe there's some cost trade-offs here, but your reliability metrics are better in loss of load expectation. This makes sense. The resources are more available for those drawdowns. And once it happens, once you have a loss of load event, it tries to charge back up as soon as possible, which maybe makes sense if this is like a critical energy reserve to mitigate reliability risks. You can see that if you don't have this state of charge target, your reliability metrics degrade rapidly. So there's this trade-off. I mean, this is a trade-off both in terms of reliability and production costs. So our next step in this analysis is to look at what that cost trade-off is. Do you get more oil generation at this higher target? Is it just a more expensive system? And and try and give some more economic numbers around it. Lastly, I want to end with looking at the 100-hour LDES versus new oil CT capacity value. So we did ELCC analysis on this. We've been looking at loss of load expectation for the reliability metrics here. But what we did is we had the systems at this 0.1 LOLE to start our ELCC analysis. We used expected unserved energy to get us back to find that ELCC, because one thing that you see when you go further out in higher solar and storage levels, or just higher battery storage as your capacity resource, is that your expected unserved energy metric can really explode. Maybe explodes a little bit of an exaggerated term, but like it grows relative to what you had in a non-storage based portfolio. So we used EUE to get back to that 0.1 system. And that's where you really see that, I mean, relative to the fuel-based units that are new and have low outage rates, LDES performs pretty well, especially in a high solar and storage system. We're talking about 70% RPS. We've got almost as much battery storage as the peak load on Oahu. So 4-hour storage has little to no ELCC in this system, but your 100-hour battery is actually pretty consistent across these different RPS levels, which we think is a pretty interesting result that we're going to dive deeper into, looking at more of those metrics and charts, and also looking at optimal portfolios. We looked at some of those portfolios with pump storage in the TVA example. We want to look at that for Oahu as well, and do some more of this analysis. So the quick takeaways, as I'm about out of time. Remember, island systems are unique. Their risk profile is different than the mainland. So this analysis is applicable to anybody in terms of like what you're going to run and the probabilistic RA work and the state of charge targets. But the way that outages and the way that the degrading fleet in Oahu contributes to the benefits you see from LDES or the benefits you see from new oil resources, it's going to be unique relative to other locations. But the principles of how to model this and the challenges still apply. Multi-day batteries in Oahu maintain a high ELCC above 55%, even at very high RPS levels with very high short duration storage penetrations. So it's a promising resource to defer oil capacity on the island. But certainly it does have limitations, as you saw in those charts, and that might be due to the portfolio, or it might be due to just the inherent energy limitations that we have on a small system. The model setup is really crucial, as you saw in those reliability metrics. Depending on what you choose, you're going to get very different results. You're going to throw out LDES and you're going to say this isn't useful, or you're going to be like, this is great, and I can get rapid decarbonization of my island system or my system in general. So I think this is still an area of continuing work, and thanks for your time.